So I'm going to use f of x instead of k of x. So this is e to 2x minus e to 4x. Good. Something different. You said 24, correct? This one.
Yes.
Perfect. Okay. So remember, we always have to try to simplify or factor. So I noticed that there is a common factor here. And the common factor is e to 2x. So I have 1 minus e to 2x. I also noticed that the domain of this function is everything. E to the x is never a problem. E to 2x or 4x is never a problem. This is always correct. All real numbers. So I have f prime of x. I have f of x. And I have the second derivative. No problems, only 0 has to be there. There is nothing else. So when I plug in 0, e to 0 is 1 minus e to 0, which is 1. 1 minus 1 will be 0. Now I have to find the limits, and I have to set the function equal to 0 to find the x-intercepts. So this is for x-intercepts. Okay, so e to 2x, 1 minus e to 2x to be 0. This cannot be 0. It's never 0. But 1 minus e to 2x can be 0. 1 equals e to 2x. And what can happen here is just x equals 0. Because only, or you can apply natural log to both sides. Natural log of 1 is 0, and this is 2x. So x is 0. So again, I already have it. There is nothing else in there. This is already in there. Now finally, I have to determine the limits. So I will determine the limit as x approaches infinity from e to 2x minus e to 4x. And I will also determine the limit as x approaches negative infinity from e to 2x minus e to 4x. Before I study the first derivative and before I study the second derivative, I need x and y intercepts. That's it. And I need the limits. So we are determining those right now. So at infinity, the bigger of the two powers is this. So this number will be larger than this one at infinity. Because it has negative sign in front, the answer will be negative infinity. Because this quantity is bigger. Now let's see this one. Here, this approaches 0, and this approaches 0. Because when x approaches a negative number, e to negative to infinity, which I shouldn't even write, will be 1 over e to 2 times infinity. Remember we said that a long time ago, 1 over huge approaches 0. So this is 0. We'll see in a moment if there is any mistake. Very easy to catch our mistakes. Zero. Therefore, this means y equals 0 horizontal asymptote at negative infinity only. This is not a horizontal asymptote, but this one is. I'll make myself a note. Y equals 0 horizontal asymptote. I exhausted the function. This is done. Now I can move on to the first derivative. And I'm on page 6. I'm going to copy the function one more time. E to 2x minus e to 4x. So now remember, when I differentiate, I get e to the function prime is e to the function times the inner function prime. So 2e to 2x. Same thing here, minus 4e to 4x. Now, when I set this equal to 0, because it will never be undefined for f prime of x to be 0, I have I will factor out the same thing, and I have 1 minus 2 e to 2x. So I factor out 2. 2 times e to 2x times 1 is this, minus 2 times 2 is 4. E to 2x times e to 2x, copy the base, add the exponents. This cannot be 0, this cannot be 0, but this can be 0. So 1 equals 2 e to 2x, or 1/2 equals e to 2x. I have no choice, I have to apply natural log. This is just the algebra. So I get 2x equals natural log of 0.5, or x equals natural log of 0.5 divided by 2. This is a negative number, this is a positive number. Let's see what we get. Where is my calculator? So natural log of 0.5 divided by 2. Negative 0.35. How will I plot that? We'll see. Negative 0.35. I go back to the table. I put negative 0.35. I put 0 here. And now I have to study the sign left and right. And I have to plug this in the function, because I need a number here. When x is negative 0.35, I need to find the y value. Okay? So, let's find the sign first. So here's my first derivative. I will plug in 0 in it. So this is 2, and 2 minus 4 is negative. And on the other side, at negative 10, it should be positive, but I want to convince myself. We can plug it in the calculator. Okay, so this time I'm going to share my screen. Go to y equals, because I need to have it in there so I can determine the values. So I will go and turn off the plots. I don't want any plots anymore. Okay. Go in there and clear all that. I will put the function in as e to 2x minus e to 4x. That is the function. And I also want to enter the derivative, which is 2e to 2x minus 4 e to 4x. I love my parentheses and I left them out. Can't believe it. Okay, so I want to determine the value at negative 0.35 only for the function. So it's 0.25. Yeah, how will I plot that? We'll see in a moment. And I also want to plug in, but this time in the second function, which is the derivative, I want to plug in negative 10. So, as expected, it's a tiny, tiny, tiny number, but positive. That's all I cared about, because I plugged in negative 10 in the derivative. So obviously, from 0 to 0.25, the function is increasing. From 4.25 to 0, yes, is decreasing, yes, is decreasing. Yeah, a sigh of relief. So from 0 it goes up to 0.25, yes, correct, and then continues to decrease to 0 and then to negative values. Awesome. Now let's see the second derivative, which I expect it to be a mess. Okay. Not really, but anyway, so this will be 4e to 2x minus 16e to 4x. And when I said the second derivative equal to 0, I would factor out 4e to 2x, and I get 1 minus 4e to 2x equals 0. These cannot be 0, but 1 can be 4e to 2x. So 1/4 equals e to 2x, and I have to apply natural log. So 2x equals natural log of 0.25, and x equals natural log of 0.25 divided by 2. And if this number is somewhere in here, then I will have to redo my table. And it may. And of course it will be. Right. Yeah. So natural log of 0.25, and I divide this by 2. Oh, excellent. Thank you so much. Negative 0.69. Yay! Good. I don't have to redo my table. But now I have to study the sign of the second derivative. So when I plug in 0 in the second derivative, I have a negative number, which means the function opens downward. But now in the second derivative, I want to convince myself that this is positive, so I'm going to plug in negative 10. I'm going to share my screen and also add the second derivative in here, and that was 4e to 2x, 4e to 2x minus 16 e to 4x. So this is the third function, and I want to see what happens at negative 10. No, I don't want to graph. I don't want to graph. Okay, so at negative 10, yes, tiny, 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 but positive. That's all I wanted to see. So it's positive. Okay, so the function holds water, and it does not. I have everything I could dream of. I don't need anything else. I don't want to see anything else. My only concern is the table. Everything else is what I like to call gibberish. Nothing. I don't care for anything else. This is it. And based on this, and I think I'm on page 7, yes. Based on this, I'm ready to graph. How will I plot? Ah! I need to determine the function value at negative 0.69, without which I cannot plot. So the function value at negative 0.69, and the function is number 1, 0.2. How will I plot that? Who knows? Nobody does. I don't. Okay, I'm kidding. So I'm going to say that this is negative 0.35, and I'm going to say that this is negative 0.69. Try to contradict me. No, I'm kidding, of course. It is what it is. I have to plot. So this is 0.2. I'm going to say 0.2 is here. And this is 0.25, so I'm going to say that 0.25 is here. I'm using, again, an invisible scale. And at 0 is 0. Okay. Opening up, coming from the horizontal asymptote, passing through this point that is an inflection point. Done. Changes concavity. It goes, of course, to a relative max. So this is an IP, and this is a relative max, positive to negative. Good. It gets to the maximum. Then it crosses the x-axis, and then continues to decrease, going down towards negative infinity. So this is e to 2x minus e to 4x. And here's the graph. Of course, this is not 100%. Why? Because I use different scale for x and y, so it looks a little confusing. But this is the shape. Now we are ready to graph. Just to double check our calculations. I do not care for, no, I didn't mean that. I will de-highlight, I don't want to graph the first derivative. I don't want to graph the second derivative. I only want to graph the function. And I know exactly where the function is. So therefore, I will go to the viewing window and I will instruct the calculator to use -2 to +2 with a scale of 0.5 and y minimum, let's say -3, and y maximum not more than 1. I know that the height is 0.25 with a scale of 0.25. I adjusted the viewing window based on my calculations and based on my graph, because otherwise I will not see anything, or pretty much nothing. Okay, now I'm ready. Aha! Yay! So it's coming from the horizontal asymptote. At somewhere at 0.2 changes concavity, turns around, gets to a maximum where at -0.35 and the height is 0.25, crosses the x-axis only and y-axis only once at the origin and goes towards -infinity. We found everything about the function. The calculator cannot tell us where the point of inflection is, but we do know it is a -0.69, comma 0.2. Okay? Can we find the maximum? Yes, we have a way of finding the maximum with second and calculations. We want maximum, number 4, and I would say you can pass the maximum. That's the left bound. The minimum not pass, so you have to give it a portion of the graph where the calculator needs to know where to look for that maximum. And when I click enter, it better be -0.35, comma 0.25. Not exactly, because we truncated, we rounded up or down. I don't remember exactly, but this should be -0.35, comma 0.25. -0.35, comma 0.25. And that's it. We knew that before the calculator gave us that. Very good example. Tedious, but good example. It was a good example for us.